Hello everyone, welcome to MES's e-learning channel. In this lecture today, we'll be starting a new topic in equilibrium, which is equilibrium in beams. So before we start, we should know what are beams. So actually, beams are the horizontal structures. These are the horizontal structures which can also take up transverse loading on it, except for the other loading conditions which are put on that horizontal structure. So as it can take transverse loading also with other loading also, so we call these structures as beam. So there are various kinds of beams. So the first one is simply supported beam. So simply supported beams are, so this AB is a beam and it is simply supported by two supports on both the ends. So that is what simply supported beam is. Cantilever beam. Now cantilever beam is only fixed at one end here and the other end is always free. So this is a cantilever beam and this is the whole length of that, which is L. This is L for simply supported beam. Now the fixed beam. Now fixed beam are supported, the length of that is fixed here and it is supported by two fixed structures and the beam is between those two fixed structures here. Fourth one is a overhung beam. Now overhung beam, if you see, this has two supports, one at the start, that is end A, and other at B, but the end of it is hanging, that is overhung. So these kind of beams are called as overhung beams. So this can also be, for overhung beams, we can also draw a structure like this. That is, it is supported at this point, let's say A, and it is supported at this point, let's say B, and both the sides are overhung. So the fifth kind of beam is a continuous beam. So if you see here, it is from A to B, if I consider as a single beam, it can be considered as a single beam or two beams connected together. So both the ends of both the beams are supported and this is why it is called as continuous, because A to B we can consider it as single beam or single structure and solve it, and then from B we can go towards C and solve it, or it can be continuous further. Like if we have D, there can be a support here and this should be a different distance. So these kind of beams are called as continuous beams. Now, as we were talking about the supports, we have different kinds of support too. So here, if you see, we have different kinds of supports, that are four different kind of supports, which is, in the roller support, the movement of the beam is not restricted from the horizontal direction. So it is only restricted from the vertical direction. So we'll only have reaction from the vertical direction. If this point is A, this would be R of A if we remove this support. That is, if this is a beam and we have a roller support at the end, so if I remove this roller support and draw a free body diagram, I'll get only one reaction, that is the vertical reaction from A, because that is the restricted side. Now next we have pin joint. Now pin joint and hinge joint have a similar kind of effect. So a pin joint allows a structure to rotate if it is fixed only at one point, and also this. So here at pin joint, the vertical as well as the horizontal motions are always restricted for hinge and pin, both the supports. So when we remove this and draw a free body diagram for a hinge and a pin joint, we would, for a hinge and a pin joint, we would get R, or this will be, let's say, VA, and this will be, let's say, H of A. That is, the support which is acting on a pin joint is at an angle because it has a tendency to rotate, and because of which the reaction which is acting on the pin joint or a hinge joint is resolved into two components. That is, one is the horizontal component and one will be the vertical component. Similarly for hinge joint also, if we remove the support, I get one reaction which will be at an angle as it is free to rotate, and so it will be resolved into two components, that is horizontal and vertical. If we have a fixed support, so if I have a fixed support also, it is restricted from both the ends, but it is not restricted from, it is restricted from horizontal and vertical direction, and it is also restricted from rotation as it is fixed. So we'll have a horizontal, and so it will have a reaction at an angle. Let's say this is RA. So it will be also be resolved into two components being HA and VA, and also as it is restricted to rotate, it will also have a couple at this point, let's say M. Now this is the fixed support. So these are the kinds of support, and whenever we have a question, so when we have a question and we need to draw a free body diagram, we should remove the supports and put the reaction which will be always unknown. So we need to find those unknown reactions. So the next is, we'll be looking at type of loadings. So there are in total 4 kind of loading. One is a zero loading, zero load condition, that is there is a beam and there is no load acting on it. So the second one is a point load. That means if, let's say, I have a beam and if that is simply supported, let us assume. So if I have a load, let's say P at this point, so the effect of the point load is only effective at this area itself. That means the application of load will be at the same distance where the P is. Let's say this distance is x, the application of the load will be x from this point, and the force applied would be P. So the load, that means the force P is applied at a distance of x. Now the second kind of loading, a third kind of loading is uniformly distributed load. We call this as UDL. So if we draw the UDL, if this is my beam which is simply supported, the UDL is represented like this. So let us assume that the distance, total distance is L, and the distance where UDL is acting is x. So we first need, before proceeding to solve a question with or any problem with UDL, we need to first convert the UDL into a point load. So here, if the loading is given as P kilonewton per meter, then this is meters. So we need to first convert this P kilonewton per meter into P kilonewton or any kilonewton. So we need to convert this into a point load condition. So how do we do that? So let's say I have the same beam drawn here. This is supported by simple supports, and so now to convert this we have a method. So if I have to calculate the force applied, that how much force will be applied when this is converted into a point load, that would be P into the distance where the UDL is being placed. That means this P into this, into x and not L, because L is the length of the beam and the UDL is not placed throughout the length of the beam. It is only till a distance of x. So this would be P into x newtons. And the point, now we need to find where this P into x load will be applied on the beam. So the point of application of where this P into x Newton load should be applied is x divided by 2 meters. That is, it will be distance where the UDL is placed divided by 2. Why divided by 2? Because it is uniformly distributed. So we assume that the application should be at the center. So when we convert this, now I'll draw that same thing. So at a distance here, that is, if we draw this, at a distance till the center of the UDL will be x by 2, and at a distance of x by 2 I'll have a load called P into x Newton, and this distance would be again x by 2, and the total distance here is L. Now the fourth kind of loading is uniformly varying load. We call this as UVL, uniformly varying load. So to represent this, so simply supported beam. So this can be drawn like this, a triangle with the forces acting downwards. Now this is, let's say, P kilonewton per meter again, and the distance over which the UVL is placed is x, and this distance is, let's say, L. So before solving this also, we need to convert this into a point load condition. So to convert this into a point load, we'll first find the force applied and the point of application. So the force applied would be how much? So as this is a triangle, so it would be P into x divided by 2. That is, if we see, if we complete this, we will get a rectangle, and this is exactly the diagonal joint between a rectangle. So this would be half of what we do in the rectangle part or the UDL part. So that would be half of P into the distance, that is the load per kilometer, to the into the distance over which the UVL is drawn. So that would be half P into x kilonewtons, as it is in kilonewtons. So here also it will be kilonewton. Now next we need to find the point of application of half P into x force on the beam. So point of application would be how much? It would be from, let's say I call this as a shorter end, and I'll call this point as the longer end. So if I calculate the point of application from this end, that is the shorter end, that is the vertex here. So shorter end, it would be 2 by 3 into the distance over which the UVL is placed. So that would be into x. And if I calculate the distance from here, it would be 1 by 3 into x. So if we see, if we add these two, it would be complete x. So 2 by 3 from this side and 1 by 3 from this side. Why did I mention like this? Because if this load is placed something like this, so we can directly calculate 1 by 3 from this side and we can get the answer directly. So now I'll convert this into point load and draw it on the similar beam. So the distance here, so now from the shorter end it is 2 by 3 x meters. So from this point at a distance of 2 by 3 x meters, there would be a force which will be half P into x kilonewtons. acting, and this distance would be 1 by 3x, and the total distance is L, meters. Everything is in meters. So this is how we solve universally varying load. So now the fifth kind of loading, this is not a different kind of loading but a combination of UVL and UDL, which is called as trapezoidal loading. So let's say I have a beam which is simply supported and I have a loading like this. This is a distance x meters and this is total distance L. And if you see, there would be always two forces mentioned. Let's say this is P kilonewtons per meter and here there would be P, let's say F kilonewton per meter. So whenever we have to convert this into a point load, we will get two forces. How? So if I draw the line from here, we can directly see that this load is a combination of UVL here on the top and UDL here on the bottom surface. So first, when we convert UDL, we'll get one force, and then when we have to convert this UVL, we'll get another force. So we'll first find for the UDL part. So the point of application for UDL, that is this much, UDL is x by 2. So the distance would be x by 2 meters and the force applied would be how much? That is P into x. So that is the force into the distance over which the UDL is placed. So here if you see this part, this force is divided into both the type of loadings, but here it is only a point of UVL and the whole thing is UDL. So we'll consider F into the distance over which that force is being placed. Next we'll solve this for UVL. So first, or else before we solve for UVL, I'll place this on a beam. So this is a simply supported beam. So here I'll first place my UDL. So from here, if I take the reference at this distance, I have my x distance over which both the loads are placed. So the UDL is placed at a distance of x by 2. So I'll draw x by 2 here, that is the half of x, and I'll place a load which is F into x kilonewtons here, as here I have mentioned kilonewton. So this is the first condition. Then I'll solve for UVL now. So point of application for UVL, so from this end, that is we call it as a shorter end. So from this end, if I calculate, it is 2 by 3 of the distance over which UVL is placed. So that is also x. And the force applied would be how much? The force applied would also be half of the load into the distance over which the force is placed. So here if we see, this side is a combination of both the UDL and UVL. So we have already solved this part. So the force which is divided by both the type of loadings, we should subtract, which we have already used for solving UDL. So what we do is, this force would become P minus F, as we have already solved this much part, and now we only have to solve this part. So F into the distance over which the force is placed. So that distance is same, that is x. So this would be my force applied. So now the distance would be from same point, that is 2 by 3 of x, and this would be how much? this is half of P minus F into X kilonewtons. So this is how we convert the different type of loading into point load, because only point load we can solve it or solve the solution problem properly. Thank you. Hope you understood.